a bit late in India. So yeah, pleasure to have Dylan Reynolds. He's from City College of New York, and he's worked on these very nice problems more recently that I've looked at on these odd systems. So the general class of odd viscosity, etc., etc. So, and he's going to tell us more about the effect of parity breaking in both classical and quantum fluids. So, Dylan, over to you. Dylan, just quickly, is it okay if people unmute themselves and ask questions in the middle of your talk so that we don't need
Yeah,
to monitor a chat box or a raised hand or something? That's
yeah,
fine,
of
right?
course. And interrupt me whenever,
So just
with any
unmute
question.
yourself. Yeah, whoever has a question, then just ask. All right, Dylan, over to you.
Perfect. Thank you very much. Thank you for the introduction. So happy to be here. As you said, I'll be talking about parity breaking in both classical and quantum fluids and sort of how the work I've done in this direction sort of ties into the bigger picture and kind of what the main story is. Let me just give a brief outline of what I'll talk about. So maybe I'll start with just some broad ideas about hydrodynamics, or at least how I like to think about it, and this will kind of set the stage for talking about the stress tensor and viscosity. And then I'll get into more details about odd viscosity specifically, which is this parity odd transport coefficient that shows up in certain systems. And then I'll maybe the first half of my talk will be about how this can be applied to active matter, and specifically 3D systems. And then some of these projects I've worked on, which are Healy-Shaw flows, which I'll explain, and then kind of an application of that, which is ferrofluids. And then maybe the second half of the talk, I'll try to get into these more the quantum version of this, which are these superfluids, which are 2D systems, and how odd viscosity, or at least something that looks like odd viscosity, can show up there. And as kind of a case study, I'll look at this fractional quantum Hall fluids that I've worked on. And at the end, maybe I'll try to tie it together. And if I have time, I might discuss polaritons also. We'll see. But maybe the goal is just to kind of see how there's a lot of different systems that have very common behavior, which is sort of this intrinsic spinniness or angular momentum at the microscopic level. And it kind of leads to this macroscopic observable effects, that are common between all these different scales and all these different systems. So let me just kind of discuss or give some examples of just spinning particles in general, as I like to call them. You can see them across all different scales. So these are some hurricanes on Jupiter and some hurricanes on Earth. What's interesting is the ones on Jupiter have collected themselves into this sort of pentagon shape, almost like not quite a crystal. But if you start to go smaller, these are starfish embryos here. And because of some sort of cellular activity on the microscopic level, it set them into rotation, and they've coalesced into this crystal structure. If you go even smaller, these are some magnetic colloids, which have been set into rotation. I'll discuss this a little bit more, but they've also kind of coalesced into this and behave as kind of a strange fluid. If you go smaller to the quantum level, you can see these sort of like a fluid of vortices in the superfluid. And you can also see this a little bit in the fractional quantum Hall effect, or just the integer quantum Hall effect, as I'll discuss. There's many different ways you can study this type of phenomena, which would be maybe you can just look at kind of like a kinetic theory and look at the collisions between particles that are spinning. This might be what you call an odd ideal gas description. For things like these starfish embryos, you might use an odd elasticity theory and look at the stress and strains in these sort of crystalline structures. But typically what I look at is just a fluid description. So in this case, all of these sort of behaviors are captured by what's called odd viscosity, which is this parity broken transport coefficient. And when I use the word parity breaking, in my head, what I really think of is there's some sort of handedness in the system. So maybe something like angular momentum or a magnetic field or something like this. Yeah, so yes?
This concept of odd viscosity is maybe like a decade old. It's very recent, right?
Yeah, right.
So, when was it first talked about? Do you have any idea?
So there was a paper by Avron, I believe, in I think the late 90s, where he started seeing connections to it. I forget exactly what his first paper was on this.
Okay,
But then kind of, yeah, I think as I'll explain, it was kind of maybe forgotten about, but if you look closely at like the symmetries of the viscosity tensor, it's allowed in certain systems. Yeah, let me think about this. I should dig up that paper. There's a kind of a seminal paper on it by Avron, where he kind of reintroduces it, I would say.
Okay, thanks.
Yeah. So let me take a step back just for a second and kind of paint a picture of fluids. So we want to study some globally conserved quantity, which I'll call Q. This could be mass, momentum, energy, entropy, angular momentum, any of these quantities. And this should give rise to some local conservation law for the density. And there's always some, so this is what we might call a continuity equation, conserving, say, mass, for example. And there's always some relation known as a constitutive relation between this flux here and this quantity. For the most part, I'm just going to focus on mass and momentum. So we have this conservation of mass equation, and there's, again, some relation between this momentum density. Let's just say that it's rho v. And then, of course, this momentum density itself has a conservation equation. So I introduce this pi ij in this way. Typically, this term here, rho vi vj, is rewritten in terms of this material derivative, as I'll have on the next slide. But this is also where the, say, viscous stress tensor would enter. And just as a note, anytime there's kind of repeated indices, I'll use this Einstein summation notation. I may kind of jump back and forth between vector notation and this index notation. If there's any confusion, just let me know. But I will ignore any thermal effects today anyway, so we'll just assume that energy is conserved automatically. So as I said, we'll typically write the governing equations in this way. So some mass conservation of momentum, and we'll introduce this material derivative. And, you know, we could have some external force. And importantly, there's this stress tensor, Tij. And it could be, in general, expressed as some gradient expansion and derivatives of velocity. And at least in what we could say is first order hydrodynamics, there's some 0th order term, which is the pressure, and then some first order term, which is, you know, a first derivative of velocity. But if we just kind of look at the structure of this, the stress tensor has two indices, I and j, and these derivatives here have two indices, k and l. So we need some 4-indexed tensor here to kind of relate the two. And in general, this viscosity tensor could be completely general, a function of density, just some function of position. Maybe there's regions of space where there's higher viscosity or less viscosity, who knows? Completely general on this point. There's a few simplifications we could make, though. If we have a compressible system, we typically supply some equation of state, which relates the pressure to the density. This is typically where maybe the speed of sound comes in. And if we had an incompressible fluid, we would just take divergence of V to be 0, at least at the level of the equations, we could say this. So let me maybe dig a little bit deeper into this viscosity tensor. Let's just start in 2D, for example. If we just have a two-dimensional compressible fluid with some general viscosity tensor, there could in principle be 16 components, right? So there's two spatial dimensions, so each index could be X or Y, there's 4 indices. So there's in principle 16 different components that could arise here. However, if we kind of restrict ourselves to fluids that are invariant under rotation in 2 dimensions, that actually only leaves 6 unique transport coefficients. So it kind of pins all these coefficients together. There's no longer 16, there's only 6. And this would be the shear viscosity, bulk viscosity, rotational viscosity. Perhaps these are more common. But there's also these 3 additional terms here, the odd or Hall viscosity, this odd pressure, and then an odd torque. If we kind of keep going and restrict to the incompressible limit, we can make the simplification. Basically, divergence of V is 0. And at the level of these indices, it means we can take delta KL to be 0 in all of these terms. And furthermore, if we want the, say there to be no internal torque in the system, we want this Tij to be symmetric. And with these restrictions, there can only be 3 viscosity coefficients that remain, which is the shear viscosity, this, say, odd viscosity, as I'll call it, and then this odd pressure term. And if we restrict it even further, let's say we want to write a fluid system that has some Hamiltonian or some maybe Poisson bracket structure. If we just take constant rho, then actually it turns out that only the Hall viscosity remains. So it's sort of, depending on how you look at it, it's one of the most interesting because it's dissipationless, and you can write a system with odd viscosity as a Hamiltonian system. Okay. That's the story in 2D, which is kind of laid out by my collaborators before I got to the, got on the investigation here. But in 3D, the system is a little bit more complicated for two reasons. One, because, well, now each of these indices can take on 3 values. So there's in principle 81 different components, at least in the compressible case. But there's also many more different like symmetries that you could impose in 3D. So for example, what you could do is just say, have a system that's rotationally invariant in a single plane, say the XY plane. And if that's the case, this actually leaves only 19 independent coefficients out of, say, the 81. And importantly, what I want to kind of draw attention to is now there's 2 different odd viscosities. So in 2 dimensions, there's just this single odd viscosity. You could call it Hall viscosity. But in 3D, if you have invariance under rotation in an XY plane, there's 2 different odd viscosity coefficients, which are kind of these ones here. And one of them is sort of just the same one from 2D, which you might call a transverse odd viscosity. But there's an additional one which has to do with, say, things in the z direction, which we could call a longitudinal odd viscosity. And typically, if you're starting from some microscopic theory, as I will discuss shortly, there's typically some relationship between these two. And a common one is that one is twice the other one, or sorry, -2 times the other one. So they usually pin together in some way, but in principle, they could be, could be distinct. And some more complicated systems, they could be completely independent. So this kind of leads into a discussion about active matter, which is someplace, or systems that kind of end up showing these sort of transport coefficients. Roughly speaking, we could say active matter is some sort of collection of agents that convert environmental energy into some sort of mechanical motion, whether it be rotation or, propelling forward like some sort of swimmer. You can see it in many different things like bacteria, cells, liquid crystals, Janus particles, or active colloids, or in general, just as I like to kind of like tell my parents, like spinny particles, a fluid that consists of spinning tops or something like this. If you have a fluid description of active matter, then typically these sort of properties are captured by viscosity coefficients. And I'd say this has been studied more extensively in 2D, 2-dimensional active matter systems, and maybe only more recently, people have been diving more deeply into the theory of 3-dimensional systems. I want to highlight a paper that I particularly like by Markovich and Lubinsky from a few years ago. They take a fluid which consists of these complex molecules. Each of these molecules themselves have kind of constituent atoms within them. And they basically assume that each of these molecules could have some sort of rotation, which is L. And they show that if this intrinsic angular momentum somehow relaxes along one direction, then actually this leads to 3D odd viscosity. And this was a very nice way to see directly how rotation at the microscopic level actually leads to this macroscopic transport coefficient, this odd viscosity.
What did you mean by angular momentum is relaxing in one direction?
So in principle, if you just look at, say, one fluid parcel, or say a water molecule or something like this, it could be spinning, along any orientation. Mm-hmm. And I guess when I say relax, what I mean is they all come into alignment. Okay. And so this L becomes a constant. Okay. Basically. But they could, in principle, each fluid could be spinning in some random direction as it's flowing. But if we take a situation where they all kind of come into alignment, then actually what they showed is that this leads to odd viscosity. So if you just write down the total momentum of each of these, say, atoms, and you do some sort of coarse graining, what they showed is that the total momentum of the system is the sum of 2 terms, the center of mass momentum of these complex molecules, but also the curl of the sort of intrinsic angular momentum And again, if you relax L along one direction and write down the governing equation for the momentum, there's this additional term here, which is L dot gradient omega. So there's, for example, if L is in the z direction, you're looking at how the vorticity changes in the z direction. Additionally, the pressure itself gets modified. And in 2 dimensions, this actually still happens, right? So if you had a 2-dimensional system with odd viscosity, you can always absorb the effects of odd viscosity into some modified pressure term. But in 3 dimensions, this term is unique, right? Because there's derivatives along the direction of rotation. And we'll see how this equation comes back again. So sort of what we were doing is wondering how can, there's in 3 dimensions, there's in principle 2 different viscosity coefficients. Is there a way to say pick out one or the other, or is there some sort of experiment that you can do to measure these odd viscosities? And can you distinguish between them in like a very robust experiment or lab setting? And this introduces the idea of what's called a Healy-Shaw cell. So roughly speaking, a Healy-Shaw cell is a fluid that's confined between 2 parallel plates, separated by some very small gap. And this leads to very nice flow patterns if you inject, say, dye on one side. And, it's a very nice tabletop setup. I think they use these maybe in like high schools or like college level physics labs just to visualize what flow looks like. And you can buy them online. And we kind of like this because it wasn't some extremely complicated lab setup that would cost like $1 million or something to, cook up. You can basically just buy it, and we could almost just do this ourselves if we really wanted to. And it's also nice because there's a very simplified equation that governs the flow, which is known as Darcy's law, which just says that the velocity in the plates, between the plates, is just proportional to this pressure gradient. And I should just say, because it's, I guess, important because we are talking about 3D, is even though, you look at this Healy-Shaw cell, it looks 2-dimensional. It is, in reality, a 3-dimensional flow. So we do have Vx, Vy, Vz. And we do enforce that on the surface of these plates that the fluid sticks, so there's no slip and no penetration boundary conditions. So if you actually look closely between the plates, there is some sort of parabolic fluid profile between the plates. We sort of average over that and just look at this, what we could say, gap average 2-dimensional flow.
So this parabolic flow and this velocity expression, it still holds when there is odd viscosity?
That's right. Yes. Okay. Yes. Right. Okay. I mean, so there was some issues that we run into if you have very complicated geometries, right? So if you have maybe like a channel that then has like a turn or something like this, or as we'll see, there's these free surface problems between 2 fluids with different viscosities. If you have 2 different fluids with some, say, free surface in a channel, and if this channel is has some complicated geometry, it's a little bit more difficult to find these exact expressions for all 3 of the components. In principle, it's possible, but I think it's, analytically much more difficult to do. But in principle, it is a 3-dimensional system. So you should find Vx, Vy, Vz in this case. Okay, so what did we do? We wanted to generalize this. So what did we do? We looked at an incompressible 3D fluid with just a general viscosity tensor that is, no symmetries imposed on the viscosity. In the incompressible case, instead of 81 in principle coefficients, it's reduced down to 64, but that's still a lot. And so, we wanted to see what happens to Darcy's law if you just go beyond shear viscosity and just say, what if you just have some general viscosity tensor? So we take these as our governing equations, just conservation of mass, conservation of momentum. And importantly, this Tij is just some, has some general stress tensor sitting here. And what we find kind of remarkably is that if we do this same sort of scaling analysis, which is assume that the gap between the plates is very small, and that these velocities vary, over much larger length scales in the xy plane than the z direction. Darcy's law is modified. Instead of just a 1 over shear viscosity here, there's this 2 by 2 matrix of viscosity coefficients. And I think it's remarkable because out of the in principle 64 coefficients, only 4 of them remain. So it kind of gives us a way to pick out just specific viscosity coefficients. It's analogous to this modified Darcy's law has been seen a little bit in flow through porous media. So if you have, say, groundwater flowing through sand, this sort of equation can show up. If, say, flow in one direction is different than the other direction, maybe the sand has some kind of tubular structure to it, so water can flow more easily in one direction. But typically it's symmetric in that case. It's also very similar to this Ohm's law with some general conductivity. For this work, or at least for these experiments that I'll outline, we're just going to look at this special case of cylindrical symmetry, which is a system that is rotationally invariant in the XY plane. And in that case, the diagonal elements of this matrix here are just the shear viscosity. And these off-diagonal elements are specifically the 3D odd viscosity. So it's just one of the two possible, parity odd coefficients. It's not the 2D Hall viscosity. It's specifically this three-dimensional, we could say longitudinal odd viscosity. And importantly, this matrix is antisymmetric, which is one of the key points. Okay, let me just give a few basic experiments that one could do to kind of probe these things. So you could just take a channel and just pump the fluid vertically upward. You could have gravity or not, this was just included for completeness. But the important thing is that if you pump the fluid vertically upward, of course, you can't have fluid flowing into the wall. So the velocity has to go up. But the result of this matrix being antisymmetric is that now there's an angle between the direction of flow and the local pressure gradient. So if you have the fluid flowing one direction, there's actually a pressure kind of pointing off at some angle, which is proportional to what I've called this eta star here, which is all of the parity breaking viscosity. What I'll probably just call is odd viscosity.
Dylan, sorry,
Yeah.
just a nice question, since this is so when you mean experiment, you mean a real experiment, is that right?
Yeah, right.
So, just out of curiosity, what's the fluid that you're pushing in? Maybe
so it's any,
I missed it, which
yeah, so it's some general fluid. I mean, this in principle could apply to many things. So take some active matter, for example, fluid that you have. Maybe you have some idea that this fluid consists of spinning particles, and put it in a Healy-Shaw cell, pump it through this channel in this way, and in principle, you would see, as I have here, some force on the channel. So these are things that would be true for many different types of systems. And this serves as a way to measure what I've called eta star here, which is basically any sort of parity breaking terms.
Right. No, so for example, since you mentioned bacterial fluid, suppose I push in bacterial fluid, but the bacteria is more run and tumble, etc. Will such a fluid work?
In principle, yes. I mean, in reality, any experiment, you might not have this perfectly uniform velocity, of course, right? And the pressure could be doing many more weird things, at least kind of locally. But at least maybe a more detailed calculation could kind of specialize this result to some system, of course. But I think this is more of just a general statement that if you have any sort of parity breaking in your fluid, this is a result that you would see.
And so that would, in principle, give you a tensor for the coefficient of viscosity, which has the right, if in an ideal world you could calculate the tensor, it would have the right symmetric antisymmetric part. That's essentially
right. So there's kind of maybe two angles. So if you have a firm grasp on the microscopic theory of your system, you could then somehow calculate what is this eta star, for example. But from the other direction, you could just put it in this Healy-Shaw cell, pump it through a channel, measure the force, and that in a sense would be a way to measure it. So you can kind of go both directions depending on, do you know more about the microscopics, or do you just want to do the experiment?
Got it. Thanks.
I have a question.
Yeah, sure.
Is it possible that the viscosity eta is 0, but eta star is not 0, like in physical systems?
In
Like
principle, yes. And I think in that case, what we found is you have to be a little more careful when you derive some of these results.
I see.
But I think in any like realistic setting, like say active matter, for example, it's always immersed in some sort of maybe carrier fluid or something that would have some shear viscosity. I think it would be very hard to have something with no
I see. Okay.
shear viscosity. But in principle, you could derive very similar results if there was actually no shear viscosity. I think it becomes a little bit interesting because this angle would go, I think, to 90 degrees.
Yeah, yeah.
And so you have to be more careful. It's possible that in those cases, creating this sort of situation is very difficult. Like it's an unstable sort of configuration, maybe. Like you try to pump the fluid up and it immediately just wants to turn. And I think this is actually a common theme that we saw is that shear viscosity tends to be sort of like a regulator for some of these very weird effects that can happen.
I see. I see. And the boundary conditions on these walls are free slip?
In this case, yes. So in all Healy-Shaw flows, once you've done this sort of like gap average move to sort of these 2D Darcy's law equation, it's fine to have the fluid slipping along these walls. And in fact, what you can do is look at sort of a zoom into the wall and write a theory for this boundary layer that develops. So if you go back and look at the full three-dimensional theory, there is actually some sort of interpolation, and it is actually no slip and no penetration on the wall, but there's some sort of like ramp up that can happen. Let's see if I can just draw. If you look near the wall and plot the velocity, it is actually 0 and then kind of quickly goes into this bulk flow. And you can do this calculation. It's not too complicated. And the odd viscosity modifies, say, the profile of it a little bit, but it doesn't change the overall result. So you can still enforce the boundary conditions.
Okay. Okay. Thank you.
Yeah. And again, this is similar to like, say, the Hall effect, where you need some sort of transverse electric field to maintain some vertical current. It's very similar in that case. Another experiment that I want to look at is this expanding bubble. So take your active matter fluid, put it in this Healy-Shaw cell, and then at some central point, begin to, say, inject a bubble of air, for example, and watch this air bubble expand. And you can measure or, say, follow the shape of this interface while it's stable. And this is typically termed Laplacian growth. It's pretty well studied. And if you want to kind of calculate the shape, at least for short times, and the pressure along this interface, it's typically given by this sort of equation. I won't spend too much time, but I just want to draw your attention here that this odd viscosity only shows up to modify this coefficient here. So it's not actually going to change too drastically what the dynamics of this interface are, but it will modify this time to form cusps. So in general, as you pump air into the center, after some time, there'll be sharp cusps that form in this bubble and it will become unstable and burst or something. So you can kind of use this to rescale time. And so you can see that odd viscosity does kind of change the time in which these cusps will form. Importantly, though, you do get some circulation far from the bubble. And you can actually measure this directly. If you know how fast the rate of change of your area of your bubble is, then you can calculate directly what the circulation is in the far field. Of course, near the interface, the velocity could be doing very strange things, but very far from the bubble, we expected this sort of behavior, some sort of spiraling behavior. The final experiment that I want to talk about real briefly is what's called the Saffman-Taylor instability. This is where you have two different fluids, say oil and water or something like this, and we assume that there's some distinct interface between them. And we want to do some sort of stability analysis on a free surface, which I've just taken to be this form. If anybody wants to discuss the details of this calculation, I'm happy to, but I don't want to get into too much. But we have some boundary conditions on the interface, so we want to match the velocities. We want to match the pressures across the interface. And if you do this with these systems with odd viscosity, what you find immediately is that there's actually some constraint on the flow angle. So for example, if your lower fluid is, say, oil, and you're pumping it directly upwards, the upper fluid has to move at some angle relative to this, directly proportional to the odd viscosity. So it would have to be, say, or you could just maybe take regular oil, but then have some strange, say, active matter system fluid of spinning particles, and it would have to move relative to that lower fluid. Additionally, the stability condition for this interface is changed. If you say pump the fluid too fast, the interface will be destroyed, become unstable. But these odd viscosity type terms can act to introduce more stability into the parameter space. So you can say pump it faster and keep the interface stable. Okay.
So has this kind of velocity direction jump been seen in experiment?
I'm not sure. We looked through the literature a little bit and haven't been able to find too many situations where there's a really good example of, say, a fluid, say, that might have odd viscosity and some distinct interface. There's a little bit, but also it's possible that creating. So I think, what should I say? If I go back, this sort of situation I think is more common experimentally. And actually, the previous, the Safman-Taylor instability, I think would apply along this interface. And there is some papers where they do this sort of thing, and you see very strange behavior of this interface here. And it sort of is trying to spiral a little bit. I think that is sort of a manifestation of this. And actually, really, this result in itself is similar, because at the central injection point, you have, say, water or air that's just going radially outward. And once you hit this fluid here, it has to move at some angle relative to that. But yeah, I think cooking up this experiment, I don't know. I'm not an experimentalist. Maybe it's difficult to cook this up. I think it usually goes the other way, where you have your active matter as a bubble and then air on the outside. And I don't think it's typically pumped. And at least in this case, I don't think I've seen any experiments where they're, like, say, pumping active matter through a channel. I don't know. I'm not sure.
Because
I do know that. Oh,
it's
sorry.
kind of intuitively hard to even grasp what's going on, because, like, does the interface turn? You said the interface tries to spiral, and if it does, like, surface tension wouldn't allow that. So maybe surface tension will stabilize the whole thing.
Yes, so there's two things to say there. First off, again, just as like at the hard wall, on this free surface, there is some boundary layer theory that you have to account for. And if you do the calculation for what's going on in this layer, it does have some thickness, this interface. And the lower fluid could be going up and the upper fluid could be going this way. And you can actually find the expression that interpolates between the two.
Okay.
This calculation I didn't do with any surface tension. I don't think that surface tension would modify it too much. This I'm maybe still looking into. I'm not entirely sure how surface tension plays into this, actually.
Okay, great. Thanks. It's interesting.
Yeah, it would be interesting. I know that, for example, in like petroleum extraction, they use similar principles to extract, say, oil or something using water. And of course, they don't want it to mix, right? They want some stable interface. So if you could somehow set your petroleum in, molecules into rotation, you might be able to keep the interface stable. I don't know. Anyway, so then we wanted to.
It stabilizes primarily because when you have the less viscous fluid next to the wall, it's a huge stabilizing effect in itself.
I see.
Yeah.
Yeah, that makes sense. Okay. Yeah.
I have a small question.
Yeah.
Does the odd viscosity break translation symmetry, for instance?
No, I don't think so.
Then I have like a bit of a silly question, that if we didn't have odd viscosity and if I have an interface between two fluids,
Yeah.
I can just change my frame of reference, and that way I can get a velocity. Right? Both the fluids will be going by the same velocity if I change my frame of reference. Here, if I do that, that doesn't seem to be like the case. Like if I'll say if I'm going down with V naught, then
Yeah, right.
So like what's happening? I'm slightly confused.
That's a good question. So you're saying if you like boost or something to a frame where this
Yeah.
interface is just staying there?
Yeah.
That's a good question, actually. I hadn't thought about this. I guess in the... That's a good question. Actually, I'm not sure I know the answer to this. I'd have to think about it a little bit more.
Okay.
I mean, at least certainly at the microscopic level, it's possible that translational invariance is being violated a little bit. I would need to think about this. Perhaps it's not an
Okay.
angle that I've thought about.
Okay. Okay.
Yeah, that made me think about a lot of things. Anyway, okay. So let me kind of finish this active matter section by just looking at this other system. We wanted to find some, sort of fluid that we can actually put in our Healy-Shaw cell, theoretically, and see if it would have these effects. And there was this nice experimental result of these magnetic colloids. So they have this group, they created some magnetic colloids, and they had this large magnetic field, and this sets all of these magnetic colloids into rotation. And what they found is that actually there was some odd viscosity, 2D odd viscosity, experimentally, but this is still just a 2D system. And so we were trying to see, is there a way when we can like generalize this to 3D? And the thing that we kind of thought of was, well, magnetic colloids are basically like ferrofluids, right? So as I will explain, ferrofluids are basically just magnetic colloids. And these are completely 3D systems. So the question was, can we find some trace of, say, 3D odd viscosity in a ferrofluid? And if we put this in a Healy-Shaw cell, do we see sort of these similar effects? What we immediately noticed was that ferrofluids are very small, very tiny. And so any sort of, I'll say like inertial effects leading to odd viscosity will wash out because they're just so tiny. But it seemed like, we looked through this book, it seems like they should possess all the essential ingredients for some sort of parity breaking. I mean, you have particles that are spinning. So is there some sort of version of ferrofluids that we can construct that would demonstrate this? And so let me just give a brief, in a nutshell, what ferrofluids are. There's some colloidal suspension. They have these magnetized particles, which are usually magnetite or hematite. They're very tiny, about 10 nanometers. There's some sort of surfactant layer that prevents clumping, that's coating them, and it's immersed in some carrier fluid. And if there's no external magnetic field, then it's just a regular fluid. You don't notice anything, just some sort of dark fluid. But once it gets near a magnet, you get this very large-scale magnetization of the fluid. And again, this sort of fits into our spirit of like cheap experiments that one could do themselves, is you can just buy this online. You don't have to, build it yourself in some complicated setup. So what's the main idea? If we zoom in on these ferrofluid particles, we can think of them as having some velocity, which if you kind of coarse grain and look at the fluid, this becomes the flow velocity. There's also, each of these particles could have some angular momentum, but they also have another vector, which is the magnetization. And in principle, the magnetization and the rotation don't have to be aligned. And then we apply some external magnetic field. And recently, as I kind of discussed earlier in this paper by Markovich and Lubinsky, what they showed is that if you write down a Hamiltonian that couples the intrinsic angular momentum to the fluid vorticity, that leads to 3D odd viscosity, as I discussed. This is much more relevant for larger magnetic colloids or large complex molecules, where the inertial effects, sort of the mass of these particles, actually manifests on the hydrodynamic scale. But for ferrofluids, they're too small. So our idea was, well, there's another vector here that you could couple vorticity to. Instead of angular momentum, you could couple it to the magnetization. So if you kind of do a very similar game, couple fluid vorticity to magnetization, write down a Hamiltonian with this additional term. Again, this is the term that Markovich and Lubinsky put in, this L dot omega term. We put down a similar term here, M dot omega, with some coupling constant. What happens? And what we found, if we just, let's skip over a lot of the technical details. If you go to this relaxed state where the magnetization is, say, pointing in the z direction, so fix the magnetic field, magnetization eventually will come to alignment with that. This will lead to this sort of 3D odd viscosity. There's a few key steps, which is take the particle size essentially to 0, take this limit, which we could call the ferrofluid limit, very small particles. And what this essentially means is that if you say did briefly change the magnetic field, it's much easier for the particles themselves to rotate than for the magnetization to like realign within the particle. They sort of just like freely move. And so you can think of the magnetization as sort of an arrow or a label that you painted on the particle. But in principle, you could have a more general theory where the magnetization and the rotation could be doing independent things. In that case, you would just have an additional term here, which comes from L, the angular momentum. And I should just stress that this is unique to 3D flows. So this Z derivative here is something that, would not show up in 2D. And we don't see this in standard ferrohydrodynamics, these fluid equations for ferrofluids. And again, I'll just point out it's very similar to what we see if you just coarse grain fluids of spinning particles. It's the same structure. But here, instead of the angular momentum, it's the magnetization that's sort of giving you this handedness. And if you put this in a Healy-Shaw cell, there's a lot of experimental work where they construct these very strange patterns. In particular, if you have a large magnetic field, say in the Z direction, and then quickly change to something that's rotating in the XY plane, you can construct these very strange patterns. And I don't think they're very well understood analytically. Of course, you can do the experiments and some numerical work, but I think there's still a lot to say here about like what are the shapes of these things. So if you just take our ferrofluid theory, put it into this Healy-Shaw cell, you get exactly modified Darcy's law, where these parity breaking terms are proportional to this coupling gamma. And again, it's some nice experiment. At one point, we wanted to do this, like buy this Healy-Shaw cell, buy this ferrofluid, tried to do the experiment ourselves. That was too complicated. But in principle, this shouldn't be extremely difficult to do. So for example, you could do this experiment here, right? So put your ferrofluid, maybe pump in water or something like this to the center. If there was no coupling, no parity breaking term here, we would just expect the ferrofluid to expand outward. But if there was this coupling between magnetization and vorticity, we might expect this spiraling behavior in the far field. And so it's perhaps nice because it's sort of just a yes-no result, right? Is there this coupling? Do you measure circulation or do you not? So let me kind of finish discussing active matter. I think odd viscosity is sort of just beginning to enter this community of active matter. And in general, the 3D effects are not well understood. There's a few other theoretical results that I find interesting. So these people put this point force here and they see this spiraling behavior. But in most of these analytical results, they always assume this relationship between the 2D and the 3D odd viscosity. And in general, I mean, they could be independent and have different effects. And I don't think much work has been done there. Additionally, even back in 2D systems with odd viscosity, I think there's some very interesting things that you can look at, which are these edge modes that propagate. I'll discuss edge modes again shortly in these quantum systems, but even classically, you expect these chiral edge modes that are protected by some sort of topology. Additionally, recently people have been looking at the drag and lift forces. So if you put some obstacle in your parity broken fluid, what sort of drag forces do you measure? And could you maybe get a lift force, right? Since there's some handedness. I would love to talk about this more, but I shouldn't delve too deep into this. Let me now move on to some quantum systems and see where odd viscosity kind of shows up in this way. Just as some background, what do I mean, quantum superfluids? It's some fluid behavior of some many-body quantum system. This could be something like helium-4, for example, which I think has this famous picture, the superfluid sort of leaking out of this chamber. Superconductivity, ultra-cold atomic gases, and Bose-Einstein condensates. There's also superfluid descriptions of these. They have certain phases that exhibit these fluid properties. Polaritons, which are sometimes termed fluids of light. I might discuss these if there's time. And also these fractional quantum Hall systems, which I'll kind of use as a case study to show how some of this works. But the general idea is we have some effective theory of our quantum system, and maybe this is described by some wave function or order parameter or something like this. And we want to map this to some hydrodynamic variables. And importantly, in most of these quantum systems, the density fluctuations are important because density is in some way related to probability. So we have to take compressible fluids. We can't typically take an incompressible limit straight away. At the end, oftentimes we can, but not initially. And the key fact that tends to show up in these systems is there's always some constraint on the vorticity. So they're going to look a lot like classical fluid systems, but there's always some additional equation that kind of constrains what the vorticity can be. So what's the general prescription, or the typical way that people have done this, is we write our wave function sort of in this polar decomposition, square root of rho times e to the I theta, and we define our velocity, our superfluid velocity, as being proportional to the gradient of this phase. And if you take this wave function into, say, the Schrodinger equation, or your nonlinear Schrodinger equation, your governing equation, if you pick out the imaginary piece, this will lead to some equation that looks like a mass conservation. And if you pick out the real part of this equation, it can be manipulated through some algebra steps to look like momentum conservation. But importantly, in these superfluids, there's never any viscosity, no shear viscosity. That's one of the important facts. Instead, what you pick up is this pressure, which is typically called quantum pressure or quantum potential. And it's a sort of complicated expression, Laplacian of square root rho over square root of rho term that shows up. So that's been done, many times in the past. So what's a little more interesting is, how does odd viscosity arise in these superfluids? Recall this continuity equation here. There's sort of a little bit of ambiguity between how you define velocity, or this relation between velocity and momentum. In principle, you could have some additional divergence-free term here, some curl of f, for example. And this is very similar to, as I discussed before, physically, there may be other sources of momentum, some center of mass momentum, plus maybe something to do with angular momentum. We'll use this as motivation to redefine the superfluid velocity in this way. So there is this gradient of phase term, which is typically done, but there's this extra curl of density term. And remarkably, what happens if you use this redefinition of velocity, this quantum pressure term here can be rewritten in terms of derivatives of velocity, this first order gradient expansion, and the resulting stress tensor looks exactly like 2D odd viscosity. So that's kind of one of the main motivations for this, and we'll see this happen. And it's almost as if the system has some angular momentum proportional to density, but I should say this isn't really the case. This isn't really what we're looking at yet, anyway. It's almost more of just what you could say a math trick to reformulate your equations so that you have a stress tensor that looks like 2D odd viscosity. And this allows us to sort of import some of our knowledge on classical fluids into these superfluids. It also helps with the boundary conditions. So this quantum pressure term, this Laplacian root rho, it's a higher order derivative, right? So if it enters as a pressure, then it enters the momentum equation with 3 derivatives, the gradient of a Laplacian. And it's hard to kind of back out what the boundary conditions on that should be. But once you have this odd viscosity looking stress tensor, it's much easier to think about, okay, no slip or no stress or no penetration of these sort of conditions. So let me kind of, if I have a little bit of time left, discuss how this shows up in the fractional quantum Hall effect.
Yeah,
Just briefly. Okay, thank you. So briefly, I'm not an expert in fractional quantum Hall systems. These fluid descriptions are sort of my window into learning about it. But what we have is some 2D system of electrons in some strong magnetic field. And if you kind of just draw like maybe a cartoon or a classical picture, what you would expect is these electrons would move in these cyclotron orbits, at least in the bulk of the sample. But near the edge, you can get this sort of like skipping behavior, right? The electrons are not able to complete their cyclotron orbits, and so they may skip along the edge. And so what one might expect, at least from just this picture, is that you would have these edge modes propagating along the edge of the sample. It was shown by Michael Stone in, say, the early 90s that the ground state of these fractional quantum Hall systems admit some sort of fluid description. And in principle, these edge modes should arise from some sort of boundary conditions on your fluid description. And this would be interesting because then all the properties of these edge dynamics could then just be written in terms of these bulk variables. You wouldn't have to defer to some sort of standalone edge theory or something like this. You could just see how the bulk flow interpolates into the edge. And additionally, this gives us a nice framework to go beyond a linear response. We can look at, say, nonlinear solitons, for example, that are moving along these boundary and that sort of thing. Okay, so how are we going to arrive at a fluid description? One way would be to start at this CSGL action, describing this bosonic matter field, and which is coupled to some external magnetic field. And importantly, you need this, what's called a Chern-Simons term, this little a here, which gives the electrons correct statistics. And to pass to a fluid description, we do something very similar. So we write this capital phi here as square root rho e to the I theta. Define our fluid velocity in terms of gradient of the phase. We should include these gauge fields here in our definition. And this term here, we will include to reformulate this quantum pressure as an odd viscosity tensor. And the resulting fluid equations, we get charge conservation, momentum conservation, this Lorentz force. And the stress tensor, as I've sort of advertised, contains this 2D odd viscosity term. And there's no quantum pressure, no derivatives of Laplacian rho or anything like this. And importantly, as I think I mentioned before, if you're ever going to describe a quantum system as a fluid, there's always this additional constraint that comes, which is we can call the Hall constraint or the quantum constraint. And in this case, it pins the fluid density to the magnetic field, the vorticity, and these derivatives of density. And depending on the system you're looking at, this will change. So for example, superfluid helium, we just have that vorticity has to be 0. These three terms are not here. If you had something like, say, these polariton systems that I've talked about, typically you don't have a magnetic field there, so this term is not here. And if you ever have something that's just bosonic, you don't need these Chern-Simons terms, and so we won't have this n here. So depending on which system you're talking about, this will look different, but in general, there will always be some additional constraint that you have to enforce. So if we want to talk about boundary conditions, let me just kind of assume that the fluid domain is just the lower half plane. There's some rigid interface, say at y equals 0. Take the energy to be basically 1/2 mv squared plus some potential, and let's see what is the rate of change of energy. And if you use this calculation, use the equations of motion, you can show that the rate of change of energy is basically can be written in terms of the off-diagonal stress tensor, these TXYs, and the Vx, right, the flow along the boundary, evaluated at the boundary. So this tilde here means it's these quantities, but evaluated specifically at y equals 0. So you can relate the change in energy, even in the bulk, right, for the whole system, to just quantities evaluated at the boundary. And then, so let's say we want energy to be conserved. There's a few options. We could take a no-slip condition, just say Vx is 0 at the boundary. But if we recall this sort of cartoon picture of these skipping orbits, we don't really want to say that straight away. That might eliminate some of this edge behavior. So instead, what we take is this no stress condition. So we allow the fluid to flow along the boundary, as long as it does so in a way that no stress is generated. And what's interesting is this no stress condition can actually be rewritten, if you use the continuity equation, can be rewritten as a different continuity equation for what we might think of as edge charge density. So this n is typically just a number density, 1 over length squared. So root of n would have something like 1 over length. And again, these tildes are quantities evaluated at the boundary. So this is essentially some sort of continuity equation for charge along the boundary. I should point out, we also just assume a no penetration condition because we don't, at this point, want any charge flowing into the boundary. So if we look at the linear response of this system, right, we will linearize the system above some mean field. We get this set of equations here. So this top one is conservation of mass, then we have conservation of momentum. This sort of first term here, omega b squared, is the Lorentz force. And this second term here is basically the odd viscosity. And I should say that even if you don't do this redefinition of velocity, if you just keep the quantum pressure, you actually get very similar looking terms. And importantly, you get the same bulk dispersion. So this is important, that this bulk dispersion doesn't actually depend on how you define velocity, which is important. But I think defining velocity in this way gives you a good way to understand maybe where it's coming from, or some sort of maybe more physical interpretation. And at this point, there is, at the level of the equations, a formal analogy. This is basically just a charged fluid with odd viscosity in some uniform magnetic field. The key difference, though, is this last equation, which is the Hall constraint. So it kind of pins them all together in a different way that would not be there if it was just some classical fluid. Also, I like writing the system in this way because it's almost like odd viscosity is a wavelength or k-dependent sort of correction to the magnetic field, right? They kind of show up in very similar terms, sort of like handedness. And so it makes me think maybe you could do some sort of like expansion where magnetic field is the zeroth order term, odd viscosity is some next order term. Like, what would these further terms represent? Anyway. So now let's look at the edge modes. So let's look for solutions to these equations that are localized near this boundary at y equals 0 and impose these boundary conditions. And through a few steps, what one can find is there's these edge modes, which we could call these chiral boson edge modes. And they have some leading order linear term 2c. And then there's these higher order terms, which one can do. And if you just do a full numerical plot, it would look something like this. And these chiral boson modes connect these two bulk bands. And I think it's just very interesting that a fluid description can capture this. And this speed of sound here is written entirely in terms of these like bulk quantities. So these potential and things like this. There's this additional term that shows up, which is known as the Kelvin mode. It turns out this is not really compatible with fractional quantum Hall fluids, but it is interesting to see because it does show up in other situations. For example, these shallow water models. So if you just have this plane model of ocean waves, the Coriolis force on the Earth is a lot like the magnetic field. And if you just look at what happens near the coast of an ocean, you also see these, say, coastal Kelvin waves, and it's very similar to that. It's a very similar situation that occurs. In the case of the shallow water model, you don't get this chiral boson because, well, you don't have odd viscosity, at least typically, and you don't have any quantum pressure, so you don't need the second no stress boundary condition. So it's interesting to kind of compare the two systems, but for the most part, this Kelvin mode does not actually represent, something in the fractional quantum Hall system. So then we wanted to go just a little bit beyond this and maybe think about what would happen if there was some dissipation in the system. Can we maybe introduce a mechanism so that energy can leak out of the system? We know the bulk dynamics are gapped, so any dissipation is going to have to happen at the boundary. So we will modify the boundary conditions so that dE dt is now less than 0 or less than or equal to 0. But we do want to maintain some sort of charge continuity at the boundary. We don't want the charge to just do whatever it wants. There should be some sort of continuity equation. And if we recall that the no stress condition was actually related to energy conservation, so this is what we will change. Right? There was this term where dE dt is integral txy vx. We took txy to be 0. And what we will do instead is we will modify this. So if you take this txy to be proportional to something with this structure, some second derivative of edge, say momentum or edge current, and introduce this coupling lambda that controls the dissipation, we see that charge continuity is maintained on the boundary. The only difference is there's kind of a modified current. And in this case, we do get dissipation. And what we actually see is if there's energy being dissipated, if we go back and look at the edge modes, now there's charge diffusion happening at the edge. And if we just kind of go beyond the linear order and look at these weakly nonlinear corrections to this, then we found we get the stochastic Burger's equation in this way, where this diffusion constant is related to, I switched to capital gamma here. This is still lowercase gamma. This is controlling the edge dissipation. And if you look at kind of how the nonlinear terms are balancing the diffusion terms, you can find this sort of leading order nonlinear correction. And if you include a noise term here, then it turns out the solution to this are just KPZ diffusion, which is this studied phenomena of, say, like a flame burning on a paper and finding the shape of this. It's this diffusion type equation. And it suggests that any sort of dissipation that's happening in these fractional quantum Hall systems are super diffusive. So there's some exponent here, which is, say, to the 3/2 or something like this. Let me see. Okay. Maybe just in the last few minutes, I can say a couple things about polaritons before I finish. This is a system that I looked at a little bit, some other quantum system that can emit a fluid description. Briefly, polaritons are created when you have these excitons in some quantum well, and then you put them between, say, two mirrors and have these photons bouncing around also. They can hybridize into what's called polaritons. The resulting particles are bosonic, so we're not going to need this additional Chern-Simons term to implement this the statistics. But what's interesting is the lifetime of these polaritons is extremely short. So if you don't continually pump the system, it will basically die out immediately within like femtoseconds or something. So it's naturally driven and dissipative, this system. Now, if you form a condensate of polaritons, it's typically described by some wave function, at least in 2D. So if we kind of do our same prescription, define fluid velocity as gradient of phase plus this additional term, put it into the governing equation, which is this Gross-Patevsky equation, and write down the fluid equations, what you'll see is there's this odd viscosity term, as usual. And what's interesting is that when you do the linear analysis, right, this linearization of the system, the continuity equation is violated. And so there's some sort of modification to the flow around these defects. And this is something that we're still sort of looking at, is how does the fact that it's driven dissipative affect the flow around these obstacles? They see it experimentally, what happens. But if you sort of look at it from the eye of odd viscosity, what does the flow around these obstacles look like in, say, the subsonic or supersonic regime, right? As the obstacle moves faster and faster, say, what is the shape of these wakes, or what is the drag force, this sort of thing. This is still something that, I'm looking at. Other future projects that maybe would be interesting in this direction is some fluid models of two-component boson systems. There was this paper by Sentel and Levin where they have these, say, like bilayer boson systems, and they can basically write down an integer quantum Hall effect for this system. It's an example of symmetry protected topological phases. And in that case, we expect there to be not just one sort of chiral boson edge mode, but actually two counter-propagating modes. And it's suspected that a fluid description of this, you could back out these edge modes from some fluid description in a very similar way. Additionally, there's some work done on these rotating Bose-Einstein condensates that are interesting for a couple of reasons. Let me just point out that why I think it's interesting is that in this case, odd viscosity actually arises in its own right. So they actually have a microscopic framework to see how odd viscosity can arise from, say, the angular momentum of these particles. And it's actually separate from quantum pressure. So as I've kind of outlined, rewriting this quantum pressure term as odd viscosity is at times just like a math trick that can help our understanding. But actually what they've shown, I believe this is Hart Goldman, has shown is that they can actually show up independently, and there can be a relation. So if you kind of look at a system that maybe has more odd viscosity or less, what happens to these edge modes? And I think more generally, what I'm interested in, at least in the superfluid direction, is there one particular choice of velocity that is the most justified? I think typically experimentally, velocity is not something that's measured. Usually it's density profiles that are measured. But if you look at, say, the dynamics of the boundaries, is there some sort of way to justify, a choice in hydrodynamic velocity? Okay, I think I should conclude here by just saying that, parity breaking appears in many different physical systems. Active systems can show up in superfluids. And in general, odd viscosity in both 2D and 3D can encapsulate some sort of properties, at least in a fluid description. And a lot of the observable effects are very common. So for example, in 3D, there tends to be this sort of spirally behavior, even in the bulk. Whereas in 2D, most of the effects are confined to the boundaries, and you sort of get these chiral edge modes that can happen. So I thank you for listening, and I'm happy to take any questions.
Thanks, Dylan. That was a really nice talk. People have questions? Jim said he had to leave.
I see.
And he says it was a nice talk.
Dylan, very nice talk. Thanks a lot. I'm absolutely new to this. Just a quick question. When you sort of introduced the superfluid model with the wave function, and then you did the usual Madelung transformation and constructed the velocity wheel, etc. So I was wondering, for finite but still small temperature, if I take the Landau two-fluid model approach for the super and the normal component,
Yes.
yeah, could that sort of approach be adapted to include these odd viscosity terms, etc., that already sort of erases something which I'm missing?
That's a good question. I mean, I think you could. Yeah, I would need to look at it in more detail, like in the sort of normal phase. I'm not sure if you get this quantum pressure term. This is what I'm not entirely sure about.
Yes, only in the superfluid, but there's this, again from memory, but there's this sort of nice coupling term which shows up between the normal and the superfluid component.
Oh, I see.
In a half, well, not half, in a reasonably ignorant fashion, sort of trying to sort of see the earlier part of your, earlier when you were talking about this magnetic colloids and the fact that you could have this sort of coupling. I was just wondering if there's some connection there which can be exploited in the normal and the superfluid component.
I would say there is. I think there's actually probably a lot to say there, to be honest. I haven't looked at it too much in this system this two fluid model that we were starting to look at. This was actually, I had thought about this. It's some idea that I've had, because when you have a superfluid with two different phases or two different species of particles, for example,
that's right.
They can be coupled in some interesting way. Let me back up here, right? They could be coupled in like various different ways. They could be coupled in the potential, or they could be coupled in this Chern-Simons term, right? Depending on like what sort of particles they are, for example. And I think you could probably capture what you're talking about, right? This normal versus superfluid phase. I think you could probably capture a lot of those effects. And it would be interesting to see what you can back out at the fluid level. And, what would happen if...
When you went through the description, you eventually end up with some sort of Gross-Pitayevsky description, right?
Right, yeah. So when you vary this action, that's what you get, exactly.
Gross-Pitayevsky, like where you have this natural way to include the odd terms. Okay. Anyway, very interesting talking and very nice work.
Yeah. Thank you.
I'll
Thank you.
stop now and do someone else. Yeah.
So I had this question for you. Basically, when you had this interface between these two fluids, you had this jump in velocity. Now, like, let's say you have only one type of particle, but that this type of particle is not homogeneously distributed. Like, we know that active particles or any kinds of particles get inhomogeneously distributed in flow, right? For various reasons, they cluster, and then there are rarer and denser regions of these particles. Right. So, if I just intuitively extend what you're saying here, it'll look as if there will be streamlined curvature just coming out of there.
Yeah, I suppose that's right. Yeah, I think that's right.
So that itself can be interesting, like the way these things can actually generate flow in directions other than the imposed pressure gradient.
Yeah, exactly. That actually would be interesting if you somehow encapsulate like the level of activity, right? If they're clustering or something in like some spatially dependent odd viscosity,
Yeah.
you might be able to see that sort of thing.
Yeah, because see, like suppose you look at motion on a rotating planet like the Earth, you have all these streamlines turning due to the Coriolis,
Right.
and now you almost have a way to design the Coriolis term by making it spatially vary.
Yeah, right. Exactly.
So it's really, really nice.
Yeah, I've thought about this, sort of describing like dynamics on the Earth. I think this is why I think I mentioned how odd viscosity is sort of like a velocity or a wavelength dependent magnetic field. Yeah, so you could probably apply something similar to the Coriolis force. Some similar. There's a lot of people who have written or have looked at what happens with Coriolis forces if your, say, ocean has odd viscosity. I think there's a lot of people who have looked at this.
Okay. Yeah, it's very interesting. Anyone else has a question? Okay, if not, can I just request Dylan to stay back for a few minutes? And Samriddhi, you're welcome to stay back or go to Patrice Legal's talk as you wish.
No, that's done. That was just before Dylan. So I moved from very classical systems where things were spinning, actually, to be honest, and then.
Okay, maybe you can stop sharing and we'll just wait for people to leave and have a chat.